On a Monday morning in August of 1883, the oceans, not slowly, not with warning, the sea gathered itself into a wall of black water, 40 meters tall in some places, and it moved toward land at the speed of a passenger jet. Entire towns were lifted from the earth, pulled into the surge, and scattered across miles of ruined coastline. More than 36,000 people died before the day was over. Some estimates suggest the number was far higher. And the cause of this catastrophe was not an earthquake. It was not a storm. It was a single island in the Sunda Strait between Java and Sumatra, an island that, by the time the sun set, had largely ceased to exist. That island was Krakatoa. The eruption that tore Krakatoa apart is considered one of the most violent geological events in recorded human history. The explosion produced a sound so loud it was heard nearly 5,000 kilometers away, on the island of Rodrigues in the Indian Ocean. That is roughly the distance from London to the middle of the Sahara Desert. People on Rodrigues reported hearing what they thought were distant cannon fire. They were hearing the death of an island from the other side of an ocean. The pressure wave generated by the blast circled the Earth not once, not twice, but at least 3 and possibly 4 times. Barographs, instruments that measure atmospheric pressure, registered the shockwave in cities as far away as Washington, London, and St. Petersburg. The wave passed over those instruments again and again, each time a little weaker, like a bell that refuses to stop ringing, but the eruption itself was only part of the horror. When the northern portion of the volcano collapsed into the emptied magma chamber beneath it, the sea rushed into the void. The result was a series of tsunamis, massive displacement waves, that radiated outward from the point of collapse and struck the coastlines of Java and Sumatra with almost no warning. The town of Merak, on the northwestern tip of Java, was struck by a wave estimated at more than 30 meters in height. Every building was destroyed. Every person in the town perished. The Dutch colonial steamship Beru was carried nearly 2 kilometers inland and deposited in a valley, 10 meters above sea level. It sat there in the jungle for years afterward, rusting quietly among the trees. A steel ship resting in a forest, a monument to a force that the human mind struggles to process. The eruption of Krakatoa ejected approximately 25 cubic kilometers of rock and ash into the atmosphere. The resulting debris clouds circled the planet and lowered global temperatures by an estimated 1.2 degrees Celsius for years afterward. Sunsets around the world turned vivid red and orange, so unusual and so persistent that fire departments in cities across North America and Europe were called out to respond to what people believed were massive fires on the horizon. Edvard Munch, the Norwegian artist, is believed by some scholars to have been inspired by these blood-red skies when he painted his famous work, The Scream. The sky itself had changed colour, and no one on Earth understood why. This was not a quiet disaster. This was the planet, speaking at full volume, from a place in the ocean that most of the world had never heard of, and the language it spoke was water, walls of it, moving at hundreds of kilometers per hour, carrying ships and houses and human beings into oblivion. By the end of tonight, you're going to understand not just what happened at Krakatoa, but why the ocean, the force that carried the destruction, remains the most powerful and least understood element of this catastrophe. You are going to understand what a volcanic tsunami truly is, how it forms, how it moves, and why the events of 1883 still shape the way scientists think about oceanic disasters to this day. You are going to understand why the waters of the Sunda Strait still hold secrets that have not been fully resolved, even after more than a century of study. And you are going to understand something far more unsettling, that what happened at Krakatoa was not unique. It was not even the worst case. It was simply the most well-documented reminder that the ocean floor is alive, that it moves, and that when it speaks, entire civilizations can be erased in hours. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what happened at Krakatoa, it is necessary first to understand the ocean, not as a surface, not as a body of blue water seen from a beach, but as a structure. The ocean has depth, it has layers, It has pressures and temperatures and zones of absolute darkness that most people never think about. And it is within these layers, within this vertical architecture of water, that the forces behind a volcanic tsunami operate. The eruption of Krakatoa was a geological event, yes, but the destruction it caused was an oceanic event. The volcano provided the energy. The ocean delivered it. The Sunda Strait, where Krakatoa once stood as a complete island, is a narrow channel of water separating the islands of Java and Sumatra in present-day Indonesia. At its narrowest point, the strait is only about 26 kilometers wide. The water depth varies, but much of the strait is relatively shallow by oceanic standards, in many places less than 100 meters deep. This matters enormously. The behavior of a tsunami, its speed, its height, its destructive potential, is directly influenced by the depth of the water it travels through. In deep ocean water, a tsunami can move at speeds exceeding 800 kilometers per hour. At that speed, the wave is nearly undetectable on the open sea. Its height may be less than 1 meter, spread across a wavelength of hundreds of kilometers. A ship floating above it might not even notice. But as the wave enters shallow water near a coastline, it slows down. The energy that was distributed across hundreds of kilometers of wavelength is compressed into a much smaller space. The wave height increases dramatically, the water piles up, and what was invisible in the deep ocean becomes a towering, churning wall of destruction at the shore. This is the fundamental physics of a tsunami. The word itself comes from the Japanese language, tsu meaning harbour and nami meaning wave, a harbour wave. The name reflects the fact that tsunamisins are often most destructive when they enter the confined spaces of harbours, bays and narrow straits. The Sunda Strait, in this sense, was one of the worst possible locations for a volcanic collapse to generate a tsunami. The narrow channel acted as a funnel, concentrating the energy of the displacement waves and directing them toward populated coastlines on both sides. To appreciate the scale of these waves, it helps to start with something familiar. A typical ocean wave, the kind generated by wind on a normal day, might have a height of 1 to 2 meters. A large storm wave might reach 10 meters. These waves are generated by wind acting on the surface of the water, and their energy is confined to the upper layers of the ocean. A tsunami is fundamentally different. It is not a surface wave. It is a wave that involves the entire water column, from the surface all the way to the ocean floor. When Krakatoa collapsed and displaced billions of tons of seawater, the resulting waves were not ripples on the surface. They were movements of the entire body of water in the strait, floor to surface, radiating outward with a force that is difficult to express in everyday language. Consider this comparison. The height of the wave that struck the town of Merak has been estimated at over 30 meters. That is roughly the height of a 10-story building. Now imagine a 10-story building made entirely of seawater, moving toward you at the speed of a commercial aircraft. That is not a flood, that is not a storm surge. That is a mass of water with the kinetic energy of a moving mountain. And behind it, more water follows. Not one wave, but a series of waves, each one pulling back before the next one arrives, each one carrying more debris than the last. The first wave kills with impact. The second wave kills with drowning. The third wave kills by burying whatever remains under tons of mud, ash, and shattered wood. The pressure exerted by such a wave is staggering. Water is roughly 800 times denser than air. A column of seawater just 10 meters tall exerts a pressure of approximately 1 atmosphere, the same pressure that the entire atmosphere of the Earth exerts on every surface at sea level. A 30-meter wave, therefore, exerts roughly 3 additional atmospheres of pressure at its base. But pressure alone does not capture the destructive force. What matters is the velocity of the water and the mass behind it. Hydrodynamic force, the force exerted by moving water, increases with the square of the velocity. Double the speed of the water, and the force increases by a factor of 4. The waves from Krakatoa were not just tall, they were fast, and they carried within them the shattered remnants of an island. Boulders, coral, volcanic rock, trees, and sediment, all of it moving at lethal speed. The ocean, in its normal state, is organized into distinct layers based on temperature, salinity, and light penetration. The uppermost layer, the epipelagic zone, extends from the surface to a depth of roughly 200 meters. This is the zone where sunlight penetrates, where photosynthesis occurs and where the vast majority of marine life resides. Below this is the mesopelagic zone, sometimes called the Twilight Zone, extending from 200 to approximately 1,000 meters. Light fades rapidly here. By the bottom of this zone, less than 1% of surface sunlight remains. Below 1,000 meters lies the bathypelagic zone, the midnight zone, where no sunlight penetrates at all. The water here is cold, typically between 0 and 4 degrees Celsius, and the pressure is immense. At 2,000 meters, the pressure is roughly 200 times atmospheric pressure. At 4,000 meters, it is 400 times. These are pressures that would crush a human body in an instant. They would collapse the hull of a conventional submarine. And yet, even at these depths, life exists, adapted, resilient, shaped by forces that surface organisms cannot endure. Below the bathypelagic zone lies the abyssopelagic zone, extending from 4,000 to 6,000 meters. And below that, in the deepest trenches of the ocean, lies the Hadal zone, named after Hades, the Greek realm of the dead. The deepest point of this zone, the Challenger Deep in the Mariana Trench, reaches nearly 11,000 meters below sea level. If Mount Everest, the tallest mountain on Earth's surface, were placed at the bottom of the Challenger Deep, its peak would still be submerged under more than 2,000 meters of water. The crushing weight of water at that depth is over 1,000 times atmospheric pressure. It is a world of eternal darkness, near freezing temperatures, and silence so complete that the concept of sound almost loses meaning. The Sunda Strait, where Krakatoa erupted, does not reach these extreme depths, but the principles are the same. The ocean is not a flat surface. It is a three-dimensional structure, and when something as massive as a volcanic island collapses into it, the energy is transmitted through that structure in ways that are extraordinarily difficult to predict. The eruption of Krakatoa occurred in a region of the ocean that is geologically among the most active on Earth, the boundary between the Indo-Australian Plate and the Eurasian Plate. This boundary runs through the Indonesian archipelago and is responsible for the chain of volcanoes that stretches across the region, a segment of the larger Ring of Fire, the horseshoe-shaped zone of intense seismic and volcanic activity that encircles the Pacific Ocean. Indonesia alone contains more than 130 active volcanoes, more than any other country on the planet. The geological forces at work beneath this region are immense. The Indo-Australian Plate is subducting, sliding beneath the Eurasian Plate at a rate of approximately 6 to 7 centimeters per year. This process generates enormous amounts of heat and pressure in the Earth's mantle, melting rock into magma, which rises through cracks and fissures in the crust to feed the volcanoes above. Krakatoa sat directly above one of these zones of subduction, fed by a reservoir of magma that had been building pressure for years before the eruption. The recorded history of Krakatoa's activity before 1883 is sparse and telling. There is evidence of a massive eruption sometime around the year 535, in which some researchers have linked to extreme weather events recorded in Europe and Asia during that period. Crop failures, famine, and the dimming of the sun described in historical chronicles. The connection between that ancient eruption and those distant effects remains debated, but the possibility highlights a critical point. Volcanic eruptions in the Indonesian archipelago do not stay local. Their effects travel through the atmosphere, through the ocean, through the very air that the entire planet breathes. In the months leading up to the August 1883 eruption, Krakatoa had been showing signs of unrest. On the 20th of May that year, the captain of the German warship Elizabeth reported seeing a column of steam and ash rising from the island. Over the following weeks, multiple ships passing through the Sunda Strait reported similar activity. Rumbling sounds, columns of smoke, pumice floating on the water. Local residents on the coasts of Java and Sumatra grew accustomed to the noise. Some were alarmed, others were not. No one understood the magnitude of what was building beneath the island. The Dutch colonial authorities, who governed the region at the time, sent a small expedition to Krakatoa in late May. The team landed on the island and observed active venting from one of the volcano's craters. They collected samples, made notes, and returned. Their report generated mild interest but no urgency. There was no system in place to warn the coastal populations. There were no seismographs on the island. There was no understanding, in 1883, of the specific mechanism by which a volcanic collapse could generate a tsunami. The science simply did not exist yet. This is a pattern that repeats throughout the history of oceanic disasters. The warning signs are present, but the framework for interpreting them is not. The ocean does not conceal its intentions. It announces them, sometimes quietly, sometimes loudly, through tremors, through changes in water temperature, through the behavior of marine life, through the subtle tilting of tide gauges. But without the knowledge to read these signals, they pass unnoticed. And by the time the signal becomes unmistakable, by the time the water pulls back from the shore, exposing the seabed, moments before the first wave arrives, it is already too late. The eruption of Krakatoa did not occur all at once. It built over a period of days. On the 26th of August, the volcano entered a phase of intense eruption, sending columns of ash more than 25 kilometers into the atmosphere. The sound was audible across the strait, and the sky over the region darkened as ash blotted out the sun. Ships in the strait reported falling pumice and waves of unusual size. The eruptions continued through the night, growing in intensity. Then came the morning of the 27th of August, 1883. At approximately 5:30 in the morning, the first of 4 colossal explosions occurred. The second followed at 6:44. The third, the most powerful, occurred at approximately 10:02 in the morning. This was the explosion that is believed to have ruptured the magma chamber and triggered the catastrophic collapse of the northern portion of the island. The fourth explosion occurred at approximately 10:52. The third explosion, the one at 10:02, is estimated to have released energy equivalent to approximately 200 megatons of TNT. For comparison, the atomic bomb dropped on Hiroshima in 1945 had a yield of approximately 15 kilotons. The Krakatoa explosion was roughly 13,000 times more powerful. The sound it produced was the loudest in recorded human history. People within a radius of roughly 160 kilometers suffered permanent hearing damage. At greater distances, the sound was described as a series of sharp reports, like artillery fire, a war no one could see, fought by forces no one could comprehend. And then the ocean moved. The collapse of 2/3 of the island displaced a volume of seawater so vast that the resulting waves reshaped entire coastlines. The tsunamis radiated outward from the collapse zone and struck the surrounding shores within minutes. Some coastal communities had less than 30 minutes between the explosion and the arrival of the first wave. Many had less than that. There was nowhere to run and nothing to run to. The terrain was flat, the elevation was low, and the wave was enormous. But here is what most accounts of Krakatoa fail to emphasize. The tsunami was not the only oceanic phenomenon generated by the eruption. The blast also produced what are known as pyroclastic flows, superheated mixtures of gas, ash, and rock that race down the flanks of a volcano at speeds that can exceed 100 kilometers per hour. Some of these pyroclastic flows from Krakatoa traveled across the surface of the water. They did not sink. They rode on a cushion of superheated gas and steam, skimming across the sea for distances of up to 40 kilometers, reaching the coast of Sumatra and incinerating everything they touched. The ocean, which is normally a barrier to fire, offered no protection. The fire came across the water. This detail, pyroclastic flows crossing the open ocean, is one of the most terrifying aspects of the Krakatoa event, and it fundamentally changed the way scientists understood the relationship between volcanoes and the sea. Before Krakatoa, the assumption was that the ocean was a natural firebreak. Water stops fire. That is one of the most basic relationships in nature. But Krakatoa proved that a sufficiently powerful eruption could project lethal heat across kilometers of open water. The ocean did not stop the destruction, it carried it. And this is where the story of Krakatoa begins to deepen, where it moves beyond a simple account of an eruption and a wave and into something far more complex. Because the events of August 1883 were not just a volcanic disaster, they were a demonstration of the ocean's role as a conduit of energy, a medium through which geological violence is transmitted, amplified, and delivered to human shores with a speed and force that defies ordinary experience. The question is not simply what happened. The question is what the ocean did with what happened. And the answer to that question is far more disturbing than most people realize. The central mystery of Krakatoa is not the eruption itself. Volcanoes erupt. That is what they do. The central mystery is the mechanism by which a collapsing volcanic island generates ocean waves capable of killing tens of thousands of people across hundreds of kilometers of coastline. And while the basic physics may seem straightforward, island falls into ocean, ocean displaces, waves form. The reality is far more complicated, far more chaotic, and in many ways, still not fully understood. When scientists began studying the aftermath of the Krakatoa eruption in the weeks and months that followed, they encountered evidence that did not fit neatly into any existing model. The wave heights recorded along the coasts of Java and Sumatra were enormous, 30 meters or more in several locations, but they were also wildly inconsistent. Some coastal towns were devastated. Others, seemingly in the path of the same waves, suffered relatively little damage. The waves arrived at different times in different locations, and their heights are varied by factors of 10 or more over distances of just a few kilometers. This was not the behavior of a simple displacement wave radiating outward in a uniform circle. Something else was happening. The Dutch colonial government, recognizing the significance of the disaster, commissioned a detailed scientific investigation. The resulting report, published in 1885 under the supervision of Rogier Verbeek, a Dutch mining engineer and geologist, remains one of the most comprehensive accounts of a volcanic eruption ever produced. Verbeek's team collected eyewitness testimony, measured wave deposits, surveyed the changed coastline, catalogued the debris, and attempted to reconstruct the sequence of events. The report runs to hundreds of pages and includes maps, diagrams, and calculations that were remarkably sophisticated for the era. Verbeek concluded that the tsunamis were generated primarily by the collapse of the volcanic edifice, the physical structure of the island, into the emptied magma chamber beneath it. As the eruption expelled vast quantities of magma, the chamber that had held that magma was left partially hollow. The weight of the island above it became unsupportable. The rock fractured, and the northern two-thirds of the island, an area of roughly 23 square kilometers, dropped into the void. The sea rushed in to fill the space, and the resulting displacement of water generated the tsunamis. This mechanism, known as a caldera collapse, is now well established in volcanology. But in 1883, it was a new concept, and Verbeek's analysis was groundbreaking. He was, in effect, providing the first scientific explanation for a volcanic tsunami, a category of oceanic disaster that had occurred many times in human history but had never been properly understood. But here's the problem. Verbeek's model, while fundamentally correct, could not explain all of the observed wave behavior. The inconsistencies in wave height and arrival time along the coast suggested that the tsunamis were not generated by a single collapse event, but by a complex series of events, multiple collapses, multiple explosions, pyroclastic flows entering the water at various points, and interactions between the waves themselves as they reflected off coastlines and interfered with one another. The Sunda Strait, with its irregular bottom topography, its islands and shoals and narrow channels, acted as a chaotic amplifier, taking the initial wave energy and redistributing it in unpredictable ways. Some locations received a concentrated burst of energy and were obliterated. Others, sheltered by subtle features of the seafloor or coastline, were spared. This is a pattern that modern tsunami scientists encounter repeatedly. The behavior of a tsunami in the open ocean is relatively predictable. The behavior of a tsunami as it interacts with a complex coastline is not. The ocean floor is not flat. It is a landscape of ridges and valleys, seamounts and trenches, submarine canyons and continental shelves. Each of these features bends, reflects, focuses, or disperses wave energy in different ways. A tsunami approaching a straight, gently sloping beach will behave very differently from a tsunami entering a V-shaped bay, which will behave differently again from a tsunami wrapping around a headland. The result is that two towns separated by just a few kilometers can experience radically different wave heights from the same event. One town is destroyed. The next is flooded but standing. The third is barely touched. The difference is not luck, it is geometry, the hidden geometry of the ocean floor. And it gets worse. The Krakatoa tsunamis were not only generated by the caldera collapse. Research conducted in the 20th and 21st centuries has revealed that pyroclastic flows, those superheated currents of gas and rock, also generated significant waves when they entered the sea. A pyroclastic flow hitting the ocean surface displaces water violently, creating its own set of waves. Because multiple pyroclastic flows entered the water at different times and from different directions during the eruption, the resulting wave field was extraordinarily complex. A superposition of waves from multiple sources, each with its own direction, speed, and amplitude. Modern computer simulations, using high-resolution models of the seafloor in the Sunda Strait, have attempted to reconstruct the wave field generated by the Krakatoa eruption. These simulations suggest that the interaction between caldera collapse waves and pyroclastic flow waves may have produced areas of constructive interference, locations where two or more waves combined to create a wave much taller than any individual source could have produced. This could explain some of the extreme wave heights observed at certain points along the coast. It could also explain the apparent randomness of the destruction, why some areas were hit so much harder than others. But these simulations are only as good as the data that feeds them, and the data from 1883 is, inevitably, limited. There were no tide gauges in the Sunda Strait at the time of the eruption. Wave heights were estimated after the fact, based on watermarks on surviving structures, the position of debris, and the testimony of survivors. People who were running for their lives, who were terrified, who may or may not have been reliable observers of the precise height of the water that was trying to kill them. The scientists working on these reconstructions are, in a very real sense, trying to read a story that was written in sand and then partially washed it away. The timeline of the eruption reveals just how chaotic and compressed the disaster was. The first major explosion occurred at 5:30 in the morning, the second at 6:44. The third, the catastrophic one, at 10:02, the fourth at 10:52. In between these major blasts, the volcano was in continuous eruption, producing a sustained column of ash and gas, generating smaller pyroclastic flows, and shaking the ground with a nearly constant series of earthquakes. The entire crisis, from the first major explosion to the final caldera collapse, lasted approximately 5.5 hours. In that time, an island was largely destroyed. More than 36,000 people were killed, and the atmospheric and oceanic effects propagated outward to encircle the globe. The human toll was concentrated on the coasts of Java and Sumatra, in the Dutch colonial settlements and the indigenous communities that lined the shores of the strait. The town of Merak, as mentioned, was obliterated. The town of Anjer, also on the Javan coast, was destroyed with almost no survivors. The town of Ketimbang, on the Sumatran coast, suffered not from the tsunami, but from the pyroclastic flows that crossed the strait, roughly 40 kilometers of open water, and engulfed the settlement. Approximately 1,000 people are believed to have died in Ketimbang from the effects of the pyroclastic flows alone. They were burned by superheated gas and ash that had travelled across the surface of the sea. The ocean, which should have been their protection, had instead served as a highway for destruction. The Dutch colonial records, while detailed by the standards of the time, likely undercount the dead. Many of the victims were from rural, non-European communities whose populations were imprecisely recorded. Some estimates place the total death toll at close to 40,000 or even higher. The precise number will never be known. What is known is that entire communities, villages, families, lineages were erased completely. There are places along the coast of the Sunda Strait where the only evidence that a town ever existed is the faint outline of foundations beneath the soil, visible only from the air. The aftermath of the eruption presented the ocean with a new landscape. Where the northern portion of Krakatoa had once risen above the waves, there was now a caldera, a vast, water-filled depression roughly 7 kilometers across. The remaining fragments of the original island, Rakata, Sertung, and Panjang, stood as remnants around the edges of this underwater crater. The depth of the caldera reached approximately 270 meters at its deepest point. The seafloor of the Sunda Strait had been dramatically altered. New shoals had formed from deposited debris. Old channels had been partially blocked. The navigational charts of the strait, which Dutch and British sailors had relied upon for decades, were suddenly obsolete. Ships attempting to transit the strait in the weeks after the eruption encountered a transformed seascape. The water was choked with pumice, volcanic rock so porous and lightweight that it floats. In some areas, the pumice rafts were so thick that ships could not pass through them. The pumice extended across vast areas of the Indian Ocean, eventually washing ashore on coastlines as far away as East Africa. Some of these pumice rafts contained the remains of human beings, bodies carried out to sea by the retreating waves, entangled in floating stone, drifting for months across open water. The atmospheric effects of the eruption were global and prolonged. The approximately 25 cubic kilometers of rock and ash injected into the stratosphere formed an aerosol layer that reflected sunlight and reduced the amount of solar radiation reaching the Earth's surface. Global temperatures dropped by an estimated 1.2 degrees Celsius and did not fully recover for several years. The vivid, blood-red sunsets persisted for months and were observed and documented around the world. In 1884, the Royal Society in London published a comprehensive study of these atmospheric phenomena, collecting reports from observers in dozens of countries. The sky had turned colours that no one alive had ever seen. Deep crimsons, brilliant oranges, purples that seemed painted rather than natural. These were not just beautiful, they were evidence of a planetary-scale perturbation caused by an island most of the world had never heard of. The Krakatoa eruption also produced a phenomenon known as a volcanic winter, a period of reduced temperatures and altered weather patterns caused by the volcanic aerosol layer. Crop yields in parts of the northern hemisphere declined. Rainfall patterns shifted. The effects were subtle compared to the immediate devastation in the Sunda Strait, but they were real and they were measurable. The eruption had connected, through the medium of the atmosphere, a small volcanic island in Indonesia to the harvests of Europe and the weather of North America. But it was the ocean that carried the most immediate and deadly consequences. And the most disturbing aspect of the Krakatoa tsunamis is not their size, nor their speed, nor their death toll. It is the fact that they were, in some ways, small by the standards of what is possible. The eruption of Krakatoa, while catastrophic, was not the largest volcanic eruption in Indonesian history. The eruption of Mount Tambora in 1815 on the island of Sumbawa, roughly 1,400 kilometers to the east, ejected approximately 160 cubic kilometers of material into the atmosphere, roughly 6 times the volume ejected by Krakatoa. The Tambora eruption killed approximately 71,000 people directly and indirectly, triggered the so-called Year Without a Summer in 1816, and produced crop failures and famine across the northern hemisphere. The tsunamis generated by Tambora were smaller than those of Krakatoa, primarily because the caldera collapse was less sudden and the geometry of the surrounding waters was different, but the eruption itself was vastly more powerful, and Tambora is not the upper limit. Geological evidence indicates that eruptions far larger than either Krakatoa or Tambora have occurred in the past. Eruptions that dwarf both events by orders of magnitude. The eruption of Toba, also in Sumatra, approximately 74,000 years ago according to scientific estimates, ejected roughly 2,800 cubic kilometers of material, more than 100 times the volume of Krakatoa. The resulting caldera, now Lake Toba, is 100 kilometers long and 30 kilometers wide. Some researchers have proposed that the Toba eruption caused a global volcanic winter so severe that it drastically reduced human populations worldwide, creating what is sometimes called a genetic bottleneck. This hypothesis remains debated, but the scale of the eruption is not in question. The implication is clear. Krakatoa was not a worst case. It was not even close to a worst case. It was a moderate to large volcanic event that happened to occur in a location and in a manner that generated catastrophic tsunamis and atmospheric effects. The ocean amplified the geological violence and delivered it to human populations with lethal efficiency. And the same ocean, with the same capacity for amplification, surrounds volcanic islands across the Pacific, the Atlantic, and the Indian Ocean. The question is not whether a similar event will occur. The question is when and where, and whether the world will be better prepared than the people of the Sunda Strait were on that August morning. Something is wrong with our assumptions about safety. Something is wrong with the idea that the ocean is simply water, inert, passive, waiting for the wind to stir it. The ocean is a transmission medium. It carries energy, and when that energy is volcanic in origin, when it comes from the collapse of an island into a void, the ocean can deliver destruction on a scale that defies ordinary comprehension. But here's what makes this truly terrifying. The Krakatoa eruption occurred at a time when the coastlines of the Sunda Strait were sparsely populated by modern standards. The total population of the affected coastal regions was perhaps a few 100,000 people. Today, the same coastlines are home to millions. The city of Bandar Lampung, on the southern tip of Sumatra, has a population exceeding 1 million. Jakarta, the capital of Indonesia, is less than 200 kilometers from the site of the eruption. The next Krakatoa, or something like it, would not kill 36,000 people. The potential toll could be measured in hundreds of thousands or more. And the next Krakatoa may already be building. In the caldera left by the 1883 eruption, a new island has been growing since 1927. Its name is Anak Krakatoa, child of Krakatoa. It rises from the same magma source that fed the original volcano. It grows, it erupts, it collapses. In December of 2018, a partial collapse of Anak Krakatoa generated a tsunami that struck the coasts of Java and Sumatra, killing more than 400 people. The wave was smaller than the waves of 1883, but the mechanism was the same. A piece of the volcano fell into the sea, and the sea responded with lethal force. The child is following in the footsteps of the parent. The ocean is waiting. The catastrophe of Krakatoa did not end with the eruption and the tsunami. It continued, in the scientific questions it raised, in the mysteries it left unresolved, and in the broader understanding of the ocean's capacity for destruction. In the decades and centuries that followed, researchers, explorers, and scientists have approached the Krakatoa event and the broader phenomenon of volcanic tsunamis from dozens of angles, each attempting to answer a different piece of the puzzle. Each answer, in turn, has revealed new complications. The more that is learned, the more it becomes clear how much remains beyond our grasp. The first major scientific investigation, as mentioned, was the Verbeek report of 1885. Rogier Verbeek was not a volcanologist in the modern sense. The discipline barely existed, but he was a meticulous geologist with access to the resources of the Dutch colonial government. His report documented the eruption sequence, estimated the volume of material ejected, mapped the new caldera, and catalogued the damage along the coasts. Verbeek identified the caldera collapse as the primary source of the tsunamis, and he estimated the wave heights at various points along the coast based on physical evidence, watermarks on buildings, the position of debris, and testimony of survivors. His work was remarkable for its time, and it remains a foundational document in the study of volcanic hazards. But Verbeek's analysis had significant limitations. He lacked the tools to model wave propagation. He had no way to simulate the complex interactions between collapsing rock, displaced water, and irregular seafloor topography. He could describe what had happened, but he could not fully explain the mechanism. The question of exactly how the caldera collapse generated waves of such extreme height, and why those waves varied so dramatically along the coast, remained open. In the 20th century, as the science of oceanography matured, researchers returned to the Krakatoa problem with new tools and new frameworks. One of the most significant developments was the understanding of wave dynamics in shallow water, the mathematical relationships that govern how a tsunami's speed, wavelength, and height change as it moves from deep water into the shallows near a coast. These relationships, described by equations developed in the 19th and early 20th centuries, allowed scientists to model tsunami propagation with increasing precision. The key insight was that a tsunami is a long wave. Its wavelength is much greater than the depth of the water it travels through, and its behavior is governed primarily by the depth of the ocean floor beneath it. This understanding led to the development of numerical tsunami models, computer programs that simulate the propagation of a wave across a digital representation of the ocean floor. These models divide the ocean into a grid of cells, each with a specified depth, and calculate how the wave energy moves from cell to cell over time. The finer the grid, the more detailed the simulation. By the late 20th century, these models had become sophisticated enough to recreate historical tsunamis with reasonable accuracy, and they were applied to the Krakatoa event with revealing results. One of the earliest and most influential modeling studies of the Krakatoa tsunamis was conducted by Katsuyuki Abe, a Japanese seismologist, in the 1970s and 80s. Abe analyzed the tide gauge records from locations around the Indian Ocean and the Pacific that had recorded the passage of the Krakatoa waves. These records, from stations in places like Batavia, now Jakarta, Aden, Port Elizabeth, and even as far as the English Channel, provided a set of data points against which the models could be tested. Abe's work helped confirm the caldera collapse mechanism and provided estimates of the volume of water displaced, on the order of several cubic kilometers. But here's the problem with these models. They assumed a relatively simple source, a single instantaneous collapse of a known volume of rock into a known cavity. The reality, as later research would reveal, was far more complex. The collapse did not happen all at once. It occurred in stages, possibly in conjunction with explosive eruptions that were themselves generating waves. The pyroclastic flows that entered the water were generating additional waves from different locations and at different times. The resulting wave field was not the product of a single source, but of multiple interacting sources, each contributing its own set of waves that combined and interfered in complex ways. In the 1990s and 2000s, a new generation of researchers tackled this complexity. Stephen Ward and Simon Day, working at the University of California, Santa Cruz, and University College London respectively, developed models that could simulate the generation of waves by landslides and volcanic collapses in 3 dimensions. Their work was not focused exclusively on Krakatoa. They also studied the potential for catastrophic landslides on volcanic islands in the Atlantic, particularly the Canary Islands. But their methods were directly applicable to the Krakatoa problem. Their models showed that the geometry of the collapse, whether the rock mass slid into the sea as a single block or fragmented into multiple flows, had a profound effect on the resulting wave characteristics. A coherent block entering the water generates a single large wave. A fragmented flow generates a series of smaller, more complex waves. The Krakatoa evidence suggested something in between, a complex, multi-stage event that produced a chaotic wave field. The numbers are striking. Ward and Day's models for a hypothetical collapse of the Cumbre Vieja volcano in the Canary Islands, a worst-case scenario that is the subject of significant scientific debate, predicted waves that could cross the Atlantic Ocean and reach the eastern coast of the Americas with heights of 10 to 25 meters. If correct, such an event could cause catastrophic damage to coastal cities from Brazil to the eastern United States. The models were controversial. Other researchers, including Philip Watts and others, argued that the wave heights were overestimated because the models did not adequately account for the energy dissipation that occurs as a tsunami travels across a wide ocean. The debate is not settled, but the underlying principle that a volcanic island collapse can generate ocean waves capable of traveling thousands of kilometers and still carrying lethal energy is not in question. Krakatoa proved it. A second major angle of investigation has focused on the specific phenomenon of pyroclastic flows interacting with the ocean. This is a subject that is both fascinating and deeply unsettling. Pyroclastic flows are among the most lethal volcanic phenomena. They consist of a dense mixture of hot gas, ash, and rock fragments that flows downhill at speeds that can exceed 150 kilometers per hour, with internal temperatures that can exceed 700 degrees Celsius. On land, they incinerate everything in their path. But what happens when a pyroclastic flow reaches the ocean? The answer depends on the nature of the flow. Some pyroclastic flows are dense enough to enter the water and sink, displacing water and generating waves much like a landslide. Others are less dense and can travel across the water surface on a cushion of steam, maintaining their lethal heat and speed for kilometers. The Krakatoa event included both types. Dense pyroclastic flows entered the strait and generated displacement waves. Less dense flows traveled across the surface of the water and reached the Sumatran coast, killing the people of Ketimbang. Research on pyroclastic flow-ocean interactions has been conducted at several volcanic sites around the world, including Montserrat in the Caribbean, where the Soufriere Hills volcano produced pyroclastic flows that entered the sea during eruptions in the 1990s. Scientists observed that the flows generated turbulent clouds of steam and ash when they hit the water, and that the resulting waves, while not as large as the Krakatoa tsunamis, were significant. The Montserrat observations provided the first modern, instrumentally recorded data on how pyroclastic flows generate ocean waves, and they confirmed what the Krakatoa evidence had suggested, that the interaction is violent, complex, and capable of producing hazardous waves. A third angle of exploration involves the geological history of the Sunda Strait itself. The strait has a long and complex volcanic history, and Krakatoa was not the only volcano to have erupted there. Geological surveys of the seafloor have revealed evidence of multiple previous eruptions and collapses, some of which may have been larger than the 1883 event. Layers of volcanic deposits in the seafloor sediments tell a story of repeated cataclysm, cycle after cycle of eruption, collapse, and regeneration. The Sunda Strait is not merely a waterway, it is a scar, a place where the Earth's crust has been torn open again and again by the forces beneath it. One of the most significant discoveries in this regard was the identification of what some researchers believe to be the remnants of an ancient caldera, a proto-Krakatoa, that predates the historical island. According to this hypothesis, the Krakatoa that existed before 1883 was itself built on the ruins of an earlier, even larger volcanic structure that had collapsed in a previous eruption, possibly the eruption around 535 that was mentioned earlier. If this is correct, then the cycle of eruption, collapse, and rebuilding at this location has been repeating for thousands of years, each cycle producing its own set of tsunamis and atmospheric effects. The current resident of the caldera, Anak Krakatoa, is simply the latest iteration of this cycle. A fourth avenue of investigation has focused on the human dimension, the question of warning and preparedness. The Krakatoa disaster occurred at a time when there was no tsunami warning system, no real-time seismic monitoring, and no understanding among the general population of the connection between volcanic eruptions and ocean waves. The people living along the coasts of the Sunda Strait had no way to know that the volcanic activity they had been witnessing for months could produce lethal waves. When the ocean pulled back from the shore, the classic precursor to a tsunami, many people walked out onto the newly exposed seabed, curious, unaware that they were standing in the path of the returning wave. In the aftermath of the disaster, and particularly after the devastating Indian Ocean tsunami of 2004, caused by a massive undersea earthquake off the coast of Sumatra, significant efforts have been made to build tsunami warning systems in the Indian Ocean and the Pacific. The Pacific Tsunami Warning Center, established in 1949 after a tsunami struck Hawaii, provides alerts for earthquakes that may generate tsunamis. The Indian Ocean Tsunami Warning System was established after the 2004 disaster. These systems rely on a network of seismographs to detect earthquakes and deep ocean pressure sensors, known as DART buoys, for deep ocean assessment and reporting of tsunamis, to detect the passage of tsunami waves in the open ocean. But here is where the answer becomes deeply unsettling. These systems are designed primarily to detect tsunamis generated by earthquakes. Earthquake-generated tsunamis typically provide some warning time. The seismic waves from the earthquake travel faster than the tsunami waves, so a seismograph can detect the earthquake minutes or even hours before the tsunami arrives at a distant coast. This time gap is the foundation of the warning system. Volcanic tsunamis are different. A volcanic collapse can generate a tsunami with little or no seismic precursor that would register on distant seismographs as a clear earthquake signal. The collapse may happen with minimal warning. The resulting tsunami travels at the same speed as an earthquake-generated tsunami, but without the advanced seismic signal that the warning systems depend on. For communities close to the volcanic source, within a few tens of kilometers, the warning time may be essentially zero. The wave arrives before any alert can be issued. This was precisely the situation during the Anak Krakatoa collapse in December of 2018. The collapse was not preceded by a large earthquake. The existing warning systems did not detect the tsunami before it struck. More than 400 people died, many of them at a beach resort where a concert was being held when the wave arrived. There had been no warning, no siren, no alert. The wave came out of the darkness. The collapse had occurred at night and washed across the lowland coast. The failure of the warning system in 2018 highlighted a critical gap in global tsunami preparedness. The systems that exist are optimized for earthquake-generated tsunamis. Volcanic tsunamis, generated by landslides, collapses, and pyroclastic flows, operate on different timescales and with different precursors. They require different detection methods, including real-time monitoring of volcanic activity, satellite observation of island morphology changes, and local sea level sensors positioned close to active volcanic islands. Some of these systems are being developed, but they are not yet widely deployed. The technology exists, the political will and the funding are often lacking. A fifth and final angle of investigation concerns the broader question of how the ocean transmits energy from volcanic events, not just in the form of tsunamis, but in the form of acoustic waves, atmospheric pressure waves, and even changes in ocean chemistry. The Krakatoa eruption produced atmospheric pressure waves that circled the Earth multiple times. These pressure waves, traveling at the speed of sound through the atmosphere, coupled with the ocean surface and generated what are known as meteotsunamis, small but detectable ocean waves caused by atmospheric pressure changes rather than by direct displacement of water. Tide gauges in the English Channel recorded these waves, faint echoes of the Krakatoa explosion, transmitted through the atmosphere and impressed upon the surface of a sea more than 11,000 kilometers from the source. The ocean also transmitted the acoustic energy of the explosion. Sound travels efficiently through water, roughly 4.5 times faster than through air, and the sound of the Krakatoa explosion was detected by hydrophones, underwater microphones, at great distances, though the technology to systematically record and analyze underwater sound did not exist in 1883. Modern research into ocean acoustics has revealed that the deep ocean contains a natural sound channel, the SOFAR channel, at a depth of roughly 1,000 meters, through which low-frequency sounds can propagate for thousands of kilometers with minimal loss of energy. An explosion like Krakatoa, occurring in a shallow strait, would have coupled energy into this channel and sent acoustic signals across entire ocean basins. The Krakatoa eruption also injected enormous quantities of sulfur dioxide into the stratosphere, where it combined with water vapor to form sulfuric acid aerosols. These aerosols, distributed globally by stratospheric winds, reflected incoming sunlight and contributed to the global cooling observed in the years following the eruption. But some of this sulfur also fell back to Earth, including into the ocean. The effect of large volcanic eruptions on ocean chemistry is an active area of research. Volcanic ash and aerosol deposition can fertilize the ocean surface with iron and other nutrients, stimulating phytoplankton blooms. These blooms, in turn, draw carbon dioxide from the atmosphere, potentially affecting the global carbon cycle. The connections between a single volcanic eruption and the chemistry of the world's oceans are subtle, diffuse, and exceedingly difficult to quantify. But they are real. The eruption of Krakatoa did not merely destroy an island and generate a tsunami. It perturbed the chemistry of the global ocean, the temperature of the global atmosphere, and the color of sunsets on the other side of the world. Each of these angles of investigation, the wave mechanics, the pyroclastic ocean interaction, the geological history, the warning systems, and the broader energy transmission, reveals a different facet of the same underlying reality. The ocean is not a passive bystander in volcanic events. It is an active participant. It amplifies, transmits, and transforms volcanic energy in ways that extend the reach of the eruption far beyond the immediate vicinity of the volcano. The eruption of Krakatoa was a local event. The disaster it caused was global. And the tools that scientists have developed to study these phenomena, the computer models, the tide gauge networks, the satellite observations, the deep ocean sensors, are powerful but incomplete. They capture the broad outlines of what happened, but they cannot predict, with confidence, the detailed behavior of the next volcanic tsunami. The ocean is too complex, too variable, too influenced by the hidden geometry of its floor and the chaotic dynamics of volcanic collapse to be fully modeled. Every simulation is an approximation. Every prediction carries uncertainty. The math is striking in its humility. For all the computational power that has been brought to bear on this problem, for all the data that has been collected, for all the progress that has been made, the honest scientific answer to the question, what would happen if Anak Krakatoa experienced a major collapse tomorrow, is, we do not know with precision. We can estimate, we can model, we can bracket the possibilities, but we cannot predict the exact wave heights, the exact arrival times, the exact pattern of destruction. The ocean keeps that information to itself until the moment arrives. There is a fact about the ocean that is so simple, so well known, and so consistently ignored that it deserves to be stated plainly. More than 70% of the Earth's surface is covered by water. Of that vast expanse, according to the most commonly cited estimates, approximately 95% remains unexplored by direct human observation. We have better maps of the surface of Mars than we do of the floor of our own ocean. We have sent more people to the surface of the moon than we have sent to the deepest point in the sea. The planet we live on is, in the most literal sense, an alien world to us, not because it is far away, but because it is below. Let that sink in. The majority of the Earth, the majority of the surface of the planet that sustains all known human life, has never been directly observed, measured, or explored. The maps we have of the ocean floor are based primarily on satellite altimetry, measurements of the height of the ocean surface, from which the topography of the seafloor can be inferred. These maps are useful, but they are coarse. The resolution of satellite-derived ocean floor maps is, in many areas, no better than 5 kilometers per pixel. Features smaller than 5 kilometers, seamounts, volcanic vents, submarine landslides, underwater ridges, may exist without our knowledge. The ocean hides them beneath a blanket of water that is, on average, roughly 3.7 kilometers deep. This ignorance has consequences. When a volcanic island like Krakatoa collapses, the behavior of the resulting tsunami is determined in large part by the topography of the ocean floor between the source and the coast. Ridges can deflect wave energy, submarine canyons can channel it, seamounts can scatter it, shallow shelves can amplify it. If the ocean floor is not accurately mapped, these effects cannot be accurately predicted. The warning that a scientist gives to a coastal community, expect a wave of this height at this time, is only as good as the map of the seafloor beneath the wave's path, and in many parts of the world's oceans, including the Indonesian archipelago, those maps are woefully incomplete. This is not science fiction. This is the current state of human knowledge about the planet we inhabit. We have explored the surface of the moon. We have landed robots on Mars. We have sent probes to the outer planets, and we do not have accurate maps of the floor of our own ocean. The implications for volcanic tsunami preparedness are profound. Indonesia is home to more than 130 active volcanoes, many of them on or near the coast, many of them on islands surrounded by shallow seas. Each of these volcanoes is, in principle, capable of producing a collapse event that could generate a tsunami. The probability of any single volcano producing such an event in any given year is low, but the cumulative probability across all of these volcanoes, over decades and centuries, is not low at all. It is, in fact, a near certainty that another volcanic tsunami will occur in Indonesia. The question is not whether, but when and where and how large. The 2018 collapse of Anak Krakatoa provided a sobering preview. The collapse involved a volume of material estimated at roughly 0.3 cubic kilometers, a tiny fraction of the volume involved in the 1883 event, and yet it killed more than 400 people. The warning systems failed. The coastal communities were unprepared. The wave was not enormous by the standards of 1883, but it was large enough to destroy homes, overturn vehicles, and sweep people out to sea. Let that sink in. A small collapse, a fraction of a percent of the 1883 event, still killed hundreds. Now, imagine a collapse on the scale of 1883, or larger, striking a coastline with a modern population density. The numbers become almost incomprehensible. The deeper truth about Krakatoa is that it was not an anomaly. It was a normal geological event, unusual in its severity, yes, but entirely within the range of what the Earth's volcanic systems are capable of producing. The Earth's crust is thin. In oceanic regions, it is only about 5 to 10 kilometers thick. Beneath it lies the mantle, a layer of hot, slowly flowing rock that extends to a depth of nearly 3,000 kilometers. The heat from the mantle drives the motion of tectonic plates, the eruption of volcanoes, the opening of rifts, and the subduction of one plate beneath another. These processes are not occasional or episodic. They are continuous. The Earth is geologically active at every moment of every day. Volcanoes are erupting somewhere on the planet right now. Tectonic plates are moving right now. The seafloor is spreading and subducting right now. And the ocean sits atop all of this, a thin layer of water on a thin crust on a planet that is, at its core, a ball of hot rock and metal. The ocean is not stable. It is not permanent. It is a dynamic system, constantly interacting with the geology beneath it and the atmosphere above it. When the geology shifts, when a volcano erupts, when a tectonic plate lurches, when an underwater landslide cascades down a continental slope, the ocean responds. And its response can be measured in lives. The case of Krakatoa illustrates another deeper truth about the relationship between human memory and geological time. The eruption of 1883 is considered a major historical event. It is taught in schools, it appears in textbooks, it has been the subject of books, documentaries, and films. And yet, in geological terms, it happened a moment ago. The 1883 eruption is separated from the present by less than a century and a half. In geological terms, that is less than the blink of an eye. The Earth has been volcanically active for billions of years, according to scientific estimates. The eruption of Krakatoa is one data point in a record that stretches back to the very formation of the planet's crust. This means that the human experience of volcanic disasters is based on a vanishingly small sample of what is possible. We have direct records of a few thousand years of volcanic activity, a tiny window into a process that has been operating for eons. The largest eruptions in the geological record, events like the Toba eruption, or the eruptions that created the Siberian Traps, or the Deccan Traps, are orders of magnitude larger than anything in recorded human history. These events ejected thousands or tens of thousands of cubic kilometers of material, altered the global climate for decades or centuries, and may have contributed to mass extinction events. They are not theoretical possibilities. They are documented geological events, recorded in the rock and sediment of the Earth's crust. The ocean has witnessed all of these events. It has transmitted the tsunamis, absorbed the ash, processed the sulfur, and redistributed the heat. It has been, throughout the planet's geological history, the primary medium through which volcanic violence is transmitted across the surface of the Earth. The ocean does not remember these events in the way that humans remember them. It does not tell stories. It does not write reports. But it carries the evidence in its sediments, in its chemistry, in the topography of its floor, for those who know how to read it. The study of these oceanic records, a discipline known as paleoceanography, has revealed that the ocean has experienced repeated, catastrophic perturbations throughout its history. Layers of volcanic ash in deep-sea sediment cores mark the timing of ancient eruptions. Changes in the chemical composition of foraminifera, tiny marine organisms whose calcium carbonate shells accumulate on the ocean floor, record shifts in ocean temperature, salinity, and chemistry associated with volcanic events. These records are incomplete, fragmentary, and difficult to interpret, but they consistently tell the same story. The ocean is a dynamic system, subject to sudden and violent disruptions, and it has been this way for as long as it has existed. The deeper truth, then, is not just that Krakatoa happened. It is that Krakatoa will happen again, not at the same location necessarily, but somewhere. An island will collapse into the sea, the ocean will rise, the waves will travel, and the question that determines how many people die will not be the size of the eruption or the height of the waves. It will be whether the people on the coast knew the waves were coming. It will be whether the warning systems worked. It will be whether the maps of the ocean floor were accurate. It will be whether the governments and communities in the path of the waves had prepared for the possibility. The answer at present is not well enough. The warning systems are improving. The maps are getting better. The science is advancing. But the gap between what is known and what is needed remains vast. The ocean covers more than 360 million square kilometers. The budget for ocean floor mapping, globally, is a fraction of what is spent on the exploration of outer space. The deep ocean sensor network that would be needed to detect volcanic tsunamis in real time, sensors positioned near every active volcanic island in the Pacific, the Atlantic, and the Indian Ocean, does not exist and is not being built. We are, in a sense, in the same position as the people of the Sunda Strait in 1883. We can see the volcano, we can hear it rumbling, we know in theory what it is capable of, but we do not have the systems in place to protect ourselves when it acts. The ocean stands between us and the volcano, and we have not yet learned to read the ocean's signals with the speed and precision that survival requires. The philosopher will note the irony. We have instruments that can detect gravitational waves from colliding black holes billions of light years away. We have telescopes that can image galaxies at the edge of the observable universe. We have particle accelerators that probe the fundamental structure of matter. And we cannot reliably predict the behavior of a wave of seawater in a narrow strait between two islands. The ocean is not distant. It is right here. It touches the shores of every continent. It fills every basin and trench and rift on the surface of the earth. And it remains, after all this time, profoundly, stubbornly, maddeningly unknown. The darkness of the deep ocean is not the darkness of space. It is a different kind of darkness, closer, heavier, more immediate. It is the darkness of something that is right beneath us, something that shapes our climate, our weather, our coastlines, our history, and our future, and yet remains, in its depths, as alien and unknowable as any world we have glimpsed through a telescope. Krakatoa was a reminder. The ocean delivered that reminder with lethal force, and the question that hangs over us now, the question that defines the deeper truth of this story, is whether we will heed the reminder or forget it, as we have forgotten so many others, until the next wave arrives. What does Krakatoa mean for us now, more than a century and 4 decades later? The immediate answer is practical. There are lessons about warning systems, about coastal development, about the monitoring of active volcanoes, about the mapping of the ocean floor. These are important lessons, and they are being learned, slowly, unevenly, imperfectly, by the institutions and governments charged with protecting coastal populations. But there is a deeper meaning, one that goes beyond the practical and into the realm of the philosophical. Krakatoa is a story about the relationship between human civilization and the forces of the natural world, forces that operate on scales of time and energy that dwarf anything in human experience. The eruption lasted hours. The tsunamis traveled for hours. The atmospheric effects lasted years. The geological cycle that produced the eruption has been operating for millennia, and it will continue to operate for millennia more. Human memory is short. Geological time is long, and the gap between them is where disaster lives. Consider the people who lived along the coasts of the Sunda Strait before the eruption. They knew the volcano was there. They could see it from their homes. Some of them had seen it emit steam and ash, but they did not leave. They did not move inland. They stayed because the coast was where the fishing was, where the trade was, where the community was. The volcano was part of their landscape, and the idea that it could, in a single morning, destroy everything they had built was not part of their conception of the world. We are not so different. Today, hundreds of millions of people live in coastal zones that are vulnerable to tsunamis, volcanic eruptions, sea level rise, and storm surges. Many of these people live near active volcanic centers. They know the volcanoes are there, they can see them, and yet they stay because the coast is where the economy is, where the infrastructure is, where the community is. The risk is abstract, the benefits are concrete, and so the choice, repeated by billions of individual decisions every day, is to live with the risk. This is not irrational, it is profoundly human. We are creatures of the present. We respond to immediate threats and discount future ones. The volcano that erupted 140 years ago is history. The volcano that might erupt 100 years from now is speculation. The job, the family, the home, these are real, and they are here, and they hold us to the coast as surely as gravity holds the ocean in its basins. But Krakatoa reminds us that the forces beneath our feet do not operate on human timescales. They do not wait for us to be ready. They do not announce themselves in terms we find convenient. The ocean does not care about our cities, our economies, our plans. It responds to the physics of displacement and propagation, and it delivers the consequences without regard for who or what is in the way. There is something humbling in this, not humiliating, humbling. The distinction matters. To be humiliated is to be diminished. To be humbled is to be reminded of one's true scale. And the true scale of human civilization, set against the forces that shaped the Sunda Strait and will shape it again, is very, very small. We are recent arrivals on a planet that has been reshaping itself for eons. The ocean was here long before us. The volcanoes were here long before us. The tectonic plates were moving long before any human being stood on a coastline and looked out at the water. This does not mean we are helpless. It means we must be honest about what we face. The monitoring of active volcanoes, the mapping of the ocean floor, the construction of tsunami warning systems, the education of coastal populations. These are not luxuries. They are necessities. They are the minimum that an honest assessment of the risk demands. And they are at present underfunded, unevenly distributed, and incomplete. There is a philosophical pause that is worth taking here. When we look at the ocean, from a beach, from a ship, from the window of an aircraft, what do we see? Most of us see a surface, a plane of water extending to the horizon, blue or grey or green, touched by wind and light. We see something that looks flat, calm, manageable. We do not see what is beneath. The 3.7 kilometers of water, on average, that separate the surface from the floor. We do not see the volcanic vents, the subduction zones, the magma chambers, the unstable slopes. We do not see the energy that is stored in the structure of the ocean itself, the potential energy of all that water, poised above the solid rock of the seafloor, ready to move when the rock shifts. The surface of the ocean is a deception. It shows us what is easy to see and hides what is difficult. And it is in the hidden depths, in the eternal darkness below the reach of sunlight, that the forces which shaped Krakatoa's destruction reside. The magma chamber that fed the volcano was beneath the seafloor. The caldera that formed when the island collapsed, filled with seawater. The tsunamis travelled through the body of the ocean. The pyroclastic flows crossed the ocean surface. Every element of the Krakatoa disaster was mediated by the ocean. Without the ocean, the eruption would have been violent but local, a mountain exploding in fire and ash, devastating the immediate area, but leaving the wider world untouched. It was the ocean that transformed a local eruption into a regional catastrophe and a global atmospheric event. The ocean is the amplifier. The ocean is the transmitter. The ocean is the delivery system, and we live on its edges, in our billions, in our cities and towns and villages, with our backs to its depths and our faces turned toward the land. We have, for most of human history, treated the ocean as a surface to be crossed, a resource to be harvested, a boundary to be charted. We have not treated it as what it is. A dynamic, three-dimensional system with the capacity to deliver geological violence to human populations with speed, scale, and indifference. Krakatoa should have changed this. Perhaps it did for a time. But memories are short, other concerns intrude. The volcano is quiet for a few decades, and the fear recedes, and the coast is rebuilt, and the cycle begins again. The question is not whether we can prevent the next Krakatoa. We cannot. The geological processes that produce volcanic eruptions and tsunamis are beyond human control. The question is whether we can prepare for it, whether we can build the systems, the knowledge, and the cultural memory needed to save lives when the ocean rises again. The answer to that question is not yet determined. It depends on choices that are being made now, and that will be made in the years and decades to come. It depends on whether we choose to look at the ocean and see what is really there. Not a surface, but a depth. Not a boundary, but a force. Not a backdrop to human history, but a protagonist in it. In the Sunda Strait, the water is calm most days. The sun rises over Java to the east and sets over Sumatra to the west, and the strait lies between them, a corridor of sea that has been travelled by traders and fishermen for centuries. The water is warm, the currents are gentle, the waves are ordinary. A person standing on the shore might look out and see nothing but horizon, a flat, quiet expanse of water that gives no indication of what lies beneath. But beneath the surface, at a depth of roughly 270 meters, there is a hole in the earth. It is the caldera left by the collapse of 1883, a circular depression in the seafloor, 7 kilometers across, filled with water and sediment. And at the center of that caldera, rising from the ruins of the old volcano, is the cone of Anak Krakatoa, growing, erupting occasionally, adding layer upon layer of lava and ash to its flanks. It is young, as volcanoes are measured. It first broke the surface of the water less than a century ago, and it is restless. It has collapsed before. It will collapse again. The magma beneath it does not rest. The tectonic forces that drive it do not pause. The ocean waits. It has done this before. It has carried walls of water across this strait and deposited them on these shores. It has swallowed ships and towns and forests and returned them as driftwood and memory. It has transmitted the energy of volcanic collapse across thousands of kilometers, bending around continents, reflecting off distant shores, arriving hours or days later as a gentle rise in the water level, a faint measurable echo of catastrophic violence. The ocean does not forget. It simply waits for the next signal. Krakatoa is a name that carries weight. It carries the weight of 36,000 lives, or more, lost in a single day. It carries the weight of a sound heard nearly 5,000 kilometers away. It carries the weight of skies that turned red around the world, of temperatures that dropped for years, of a pressure wave that circled the planet again and again, like a pulse that would not stop. It carries the weight of water, billions of tons of it, rising from a narrow strait and crashing onto shores where children played and fishermen mended their nets. And it carries a warning. Not a loud warning, not a dramatic one. A quiet warning, carried in the sediment of the seafloor and the chemistry of the atmosphere and the fading memory of survivors' descendants. The warning is simply this: the Earth is not finished. It is not settled. The forces that built Krakatoa and destroyed it are the same forces that built the land we stand on and the ocean basins we sail across. They are patient forces, operating on timescales that make a human lifetime seem like a breath. But they are not gentle. When they act with a violence that our language struggles to describe and our minds struggle to contain. The ocean carries this violence. It stores it in the potential energy of its depth. It transmits it in the kinetic energy of its waves. It delivers it to the shores where we build our homes and our harbors and our lives. The ocean is not hostile. It is not malevolent. It is simply vast and deep and capable of movements that reduce human structures to debris in moments. We know this. We have known it since 1883 and before. We knew it when the Indian Ocean tsunami of 2004 killed more than 220,000 people. We knew it when the 2011 tsunami struck Japan and overwhelmed the defenses of one of the most technologically advanced nations on Earth. We know it when Anak Krakatoa rumbles and the monitoring stations record the tremors, and the scientists issue their cautious assessments. We know it, and we continue to live on the coast, because the coast is where we have always lived, and because the ocean, on most days, is calm. The calm is real, but it is not permanent. It is a pause between events, a rest between movements in a symphony that the Earth has been playing for longer than human history can record. Krakatoa was one movement. The next movement will come. It may not come from the same place. It may not come in the same way, but it will come, because the forces that produce it are as fundamental as gravity, as relentless as the heat of the planet's interior, as certain as the movement of tectonic plates across the face of the Earth. And when it comes, the ocean will rise, as it rose in 1883, as it rose in 2004, as it rose in 2011. The water will gather itself into something that is no longer a surface, no longer a calm expanse, no longer a place of beauty and peace. It will become a force a wall, a weight, a moving mass of destruction that obeys no human law and respects no human boundary. The ocean is patient. The ocean is deep. The ocean remembers what we forget. And in the darkness below the sunlit surface, where the pressure is immense and the silence is absolute, the floor of the earth is still moving, still shifting, still feeding magma into the vents and chambers that will one day produce the next eruption, the next collapse, the next wave. The water is calm tonight, the strait is quiet, the stars reflect on the surface of the sea, and the cone of Anak Krakatoa rises dark against the sky, a shadow on the horizon. Growing, listen closely. Beneath the silence, the earth is breathing.